Hello, this is Shoot Socrates, and in today's video, we're going to look more into systems of linear equations. This is the second video about systems of linear equations. So if you haven't seen the first video yet, now would be a good time to stop this video and look at that first video before watching this video. We have a lot to do today, so let's see what is on our agenda. We are going to use systems of linear equations to ask if a vector is a member of a span of a set of vectors. We will construct a system of linear equations from this problem, and we're going to find the REF of this system in two different ways. The first way will be the classical way, which is called the Gauss Jordan Algorithm, and the second way is something a little bit more clever. We will learn how to choose row operations wisely so that you can avoid fractions and make things simpler for you, if that's possible. We are going to ask, well, are there always solutions to a system of linear equations? And how do we know when there are solutions or when there are no solutions? And finally, we will look at a special family of matrices called identity matrices. And when these matrices show up in your REF, then something special is going to happen. So let's get to it with the first topic. We are going to ask the question. Suppose you have a set of vectors. So let's call them v1, v2 through vn. And they are all from a Euclidean space Rm. And you have a fixed vector b also from Rm. So we can ask, is this vector b a member of the span of S? And as a reminder, the span of S, which is the span of v1 through vn, is made of all possible linear combinations, x1 v1 plus x2 v2 through xn vn, where the coefficients x1, x2 through xn are all real numbers. Here's an example, and it's a big one. Suppose that we have this set of 6 vectors from R5. So those vectors are v1 through v6, and we see them listed here. We are going to decide if this vector b, 5, 6, 10, 5, negative 6, which is also from R5, is a member of the span of S. And if it is, we are going to find the simplest linear combination of v1 through v6 that adds up to this vector b. So based on the definition of span, this comes down to looking for 6 coefficients, x1 through x6, such that b is a linear combination x1 v1 plus x2 v2, and so on through x6 v6. So now that this equation has been set up, we are going to bring the scalars inside the vector. So x1 times v1 becomes 7x1 minus 4x1, 3x1 minus 5x1, and 2x1 by simply bringing the scalar inside the vector. So we do that to each of the other 5 vectors, and we get this very long vector sum. So finally, we perform the vector sum. We have 7x1 plus 5x2 plus 3x3 minus 5x4 minus 3x5 plus x6, which we will find in the first component of this vector. And we are going to do exactly the same thing for each of the other 5 components of this vector. Now, because we have this vector equation, we know that the first component on the left should be equal to the first component on the right. So that means that 7x1 plus 5x2 plus 3x3 minus 5x4 minus 3x5 plus x6 has to be equal to the first component, which is 5. So here we get the first equation in a system of linear equations. There are 5 components on each side of this vector equation, so we get a total of 5 equations, and we have 6 variables, x1 through x6, we want to solve for all of them. In our first video, we said that this system is represented by an augmented matrix. So to write that matrix down, all we do is write the coefficients from each equation in the appropriate columns, and instead of an equal sign, we have a vertical bar to represent that equal sign. So we have an augmented matrix made of 5 rows and a total of 7 columns, 6 for the variables and 1 for the right side. We don't count the vertical bar as a separate column. So next up, we are going to go to our online calculator to find the REF of this matrix in 2 different ways. As I mentioned before, we are going to use first the Gauss Jordan algorithm. You'll find it on page 83 in section 1.5 of the 4th edition. And we are also going to find it by making smart choices when we perform row reduction. So to remind you first, what is the REF, or the reduced row echelon form of a matrix? How do we know that we have found it? Well, there are 4 qualifications, and if you satisfy the first 3 qualifications, you get a matrix which is in row echelon form only. So the first requirement is that all the rows consisting entirely of zeros are found at the bottom of the matrix. Now, the first non-zero entry of any row has to be the number 1. We call this entry a leading one, and if the next row is also a non-zero row, then its leading one has to be to the right of the previous leading one. So the 4th condition will make the matrix into an REF, and that is all the entries above a leading one also have to be 0. So let's proceed to our online calculator. So here we are, and in our last video, we used the row operation calculator. So to see the Gauss Jordan algorithm at work, we are going to use this routine, which will transform a matrix automatically for us into the REF. Okay, so our first step is to input the number of rows, which we said is 5, and the number of columns, which is 7. All right, so here's our blank matrix. Okay, so I've gone ahead and entered our matrix to save us time, and we are going to click Submit. Ooh, okay. So there's quite a bit going on in this page, and let's take a look at what happened here. Right, so the first thing the computer did was to multiply the first row by 1/7. Same thing as divided by 7. So that turns the 7 into a 1. So that's what the Gauss Jordan algorithm does. If your number in the upper left corner is not 0, you just divide by that number so that you'll get your leading one right away. So now you get to clear the 4 numbers which are below that leading one. So add 4 times row 1 to row 2 to make that -4 0. Add -3 times the first row to turn that 3 into a 0. What's next? Multiply the first row by +5 and add it to the 4th row. And lastly, we are going to multiply the first row by -2 and add it to the 5th row. So now, all the numbers below the leading one are zeros. But notice that there are 7s all over the place, fractions, okay? And that's because the first row was divided by 7. So this is not what you want to do by hand if you are finding the REF of a matrix without any technology. So what's next? We want a leading one in the second row. So now we are going to turn the -1/7 into a +1, and that is by multiplying the second row by -7. So at least the fractions are gone from the second row. So what are we going to do next? That leading one is going to clear the numbers in column 2, again by multiplying the second row by a suitable constant and adding it to the next rows. So to clear the minus 8/7, we will multiply the second row by positive 8/7 and then add it to the third row. So now we have not just 1 0, but 2 zeros in the third row. So you keep doing this. You now have to add 3/7 times row 2 to row 4 and negative 11/7 times row 2 to row 5. So that is this operation. Again, we have 2 zeros. Ooh. And then finally for the last row, we also have 2 zeros. So notice what happened here. We do not have a possibility for a leading one in the third column because the third column is zeros below row 2. So our next leading one is going to come from the fourth column in row 3. So we will divide the third row by 7. But luckily, all of those numbers, I believe, are divisible by 7. Yes. So we get all integers. 1, -8, 6, and -9. Okay, so now that we have that leading one, we have to turn the 2 and the -10 into zeros. So we will multiply row 3 by -2, add to row 4, multiply row 3 by +10, add to row 5. So that will, that turned row 4 entirely into zeros. And how about row 5? Entirely into zeros also. So after we have row 3, we have nothing in row 4 and row 5. So this ends the first half of the Gauss Jordan algorithm. Up to this point, it's called Gaussian elimination or Gaussian reduction. So now we are going to use these leading ones, this time going from right to left to clear the entries above each leading one. Why right to left? If you start on the left, then you're going to have to recompute all of these numbers. And that includes that 6 over here. Okay? But if you start with this leading one, then the 6 will turn into a 0. The -5/7 will turn into a 0. So that will be less work when you get to this leading one because zeros will stay 0. Okay, so the next step will be to turn that 6 into a 0. So we multiply row 3 by -6 and we add to row 2. All right, so we get 0 there. These are not going to turn into zeros. It's only the numbers above and below the leading one which we can expect to turn to zeros. So now we will clear the -5/7, multiply row 3 by +5/7, and add to row 1. Okay, so that is now a 0. So I believe we are down to the last step. We are now going to use this leading one to turn the 5/7 to 0. So multiply row 2 by -5/7 and add to row 1. Yes, that is indeed our last step. We have reached the bottom of the page, and that entry is now a 0. So as you can see, this matrix is now the final REF. All rows of zeros are found at the bottom of the matrix. Each entry, the first non-zero entry in each row is a 1, which we call our leading one, and every entry above and below our leading one is a 0. So as promised, we are going to find the REF a second way, and that is by making smart choices to perform the next row operation. So we're going to use the same routine that we did last time, the row operation calculator. So we have 5 rows and 7 columns. And once again, I will take a break and input the numbers for us. Okay, here they are. So I'm going to click Submit. And there is our calculator. So reminder, we are allowed to perform 3 kinds of row operations. And now comes the hard part, choosing wisely what we are going to do next. So in Gauss Jordan, the computer divided the first row by 7. Not very smart if you're doing it by hand. Is there a better way to make a leading one? There are actually lots of ways. Let's do this one. There's a 3 in the 3rd row and a 2 in the 5th row. So how about we just subtract the 5th row from the 3rd row? 3 minus 2 will get us 1. So that means add -1 times the 5th row to the 3rd row. Let's do it. Okay, so we have our leading one now in the 3rd row. So let's exchange that with the 7, interchange 1st and the 3rd row. Okay, and now we will use the 1st row to eliminate -4, 7, -5, and 2. Add 4 times the 1st row to the 2nd row. Add -7 times the 1st row to the 3rd row. Add 5 times the 1st row to the 4th row. And finally, add -2 times the 1st row to the 5th row. Okay, so our first column is now perfect, and we have to work on this smaller submatrix. Is there a good way to make a leading one here? Well, we can at least make a 0, so let's add 2 times the 5th row to the 4th row. All right, so we get a 0 there, and another 0 here. Okay, so how about the leading one? Well, okay, I got something. Here's -11 and 7. So what if we doubled it to get 22, positive 22, and then we subtract 3 times 7? Okay, so let's multiply the 2nd row by -2, and we get 22, and now add -3 times the 5th row to the 2nd row. Okay, so there's our leading one, and now we clear the 19 and the 7, multiply the 2nd row by -19. Oh, I'm sorry, we will add -19 times the 2nd row to the 3rd row. That's better. And add -7 times the 2nd row to the 5th row. Okay, there we go. And that's nice. We have a -1 here. So all we have to do is multiply the 4th row by -1 and then exchange it with the 3rd row. And then we clear the -43 and the -16. So add 43 times the 3rd row to the 4th row. Ooh, all zeros. So that happened before also. And add 16 times the 3rd row to the 5th row. All zeros as well. So now all we have to do is use each leading one from right to left to turn all the entries above it also into zeros. Okay, so we add -2 times the third row to the second row. So now everything above that leading one is a 0. And lastly, we will add 2 times the second row to the first row. All right, so there it is. And of course, this is exactly the same REF that we got earlier using the Gauss Jordan algorithm. So now we're going to go back to our lecture notes, and we're actually going to find solutions to our system of equations. Now, I don't want to write the REF that we got from our online calculator, so I'm going to make Scientific Notebook do it for us. So this is our augmented matrix. I'm going to delete this column because otherwise Maple will freak out. Maple is the computational engine for Scientific Notebook. And all we have to do is click on Compute, which is hiding up here. Go to Matrices and look for Reduced Row Echelon Form. Ooh. So there's the same REF that we got last time. So our leading ones are in column 1, column 2, and column 4. So let's write down our leading variables are x1, x2, and x4. So we said if a variable is not a leading variable, then it is a free variable. So we have a free variable in column 3, column 5, and column 6. Our free variables are x3, x5, and x6. So quick check, all 6 variables appear here exactly once. x1, x2, x3, x4, x5, and x6. So next we're going to write each of these rows as an equation involving our 6 variables. So our first row says that x1 plus 4, that's x3 because it's in the third column, minus 4x5 plus 3x6 equals 0. Okay, so there's nothing wrong with having 0 on the right side. Our second equation is x2 minus 5x3 minus 3x5 plus 2x6 equals -8. And our final equation is x4 minus 8x5 plus 6x6 has to be equal to -9. So let's double check. That's x1, 4x3 minus 4x5, 3x6 equals 0. x2 minus 5x3, 0, minus 3x5 plus 2x6 is -8. And x4 minus 8x5 plus 6x6 equals -9. Okay, so from these 3 equations, we are now ready to form our solution vector. So I've gone ahead and labeled it. We have x1 through x6, and we're going to fill in the actual solution vector. So the first thing is to remember who are the free variables, x3 and 5 and x6. So let's copy that at the bottom, where x3, x5, and x6 are any real numbers. They are our free variables. Okay, so that will tell us, that will remind us that 3, 5, and 6 are free. So we will put x3 in our third component. That's our third component. x5 is free. Fourth fifth component, and x6 is free, last component. There we go. So those are our free variables, and they are in their correct place. Third component, fifth component, and sixth component. So now that we have that, we can solve for the leading variables in terms of the free variables. So who is x1? We will move all of these to the right, and we will get 0 minus 4x3 plus 4x5 minus 3x6. So we can write that down in the correct place. x1 is minus 4x3 plus 4x5 minus 3x6. There we go. Next, who is x2? Minus 8 is on the right side. And we will move these variables to the right. So we will have plus 5x3 plus 3x5 minus 2x6. Okay, last equation. x4, you have minus 9 on the right, and it stays there. So we have minus 9 plus 8x5 minus 6x6. But let's remember that our original question or goal was to decide whether or not our vector B is a member of the span of S. Now, we were able to find solutions for x1 through x6, so the answer is yes. It is a member of the span. And now that we know that, we want to find the simplest linear combination of v1 through v6 that add up to B. Now, as we said in the last video, the simplest solution can be obtained by setting all the free variables equal to 0. So we will set x3, x5, and x6 all to 0. And so we get, as our solution vector, let's copy this whole thing. All of the three variables will be 0. So nothing survives in the first component. All we get is 0. In the second component, only the minus 8 survives. In the third component, x3 is 0, a free variable. Fourth component, minus 9 survives. Fifth component, x5 is 0. Last component, also 0. So we only have 2 non-zero entries in our solution vector. So from here, we can now get the simplest linear combination of v1 through v6 that add up to B. Our coefficients are negative 8, and that is the coefficient for v2 because that is in x2. Minus 9, and that is the coefficient for v4. Okay, so let us now check that this is going to work. So I have copied here the original vector equation that we have, and also the augmented matrix corresponding to this vector equation. This is what I want you to notice. This is our v1, 7 minus 4, 3 minus 5, 2. Notice that v1 appears in column 1. Who's v2? 5 minus 3, 1 minus 4, 3. 5 minus 3, 1 minus 4, 3. So v2 appears in the second column. What do we want to do? We want to form this linear combination, minus 8v2 minus 8v4. So here's what I'm going to do. I'm going to take negative 8 and I'm going to multiply it by V2, which we find here in column 2. So I'm going to copy that here, and I want minus 9 multiplied by V4, which is found here in column 4. Okay, so we already typed out this matrix. Why should we type V2 and V4 all over again? They're found in this matrix. Is that correct? Boom! We get 5, 6, 10, 5, minus 6. So that is indeed our vector B. Okay, great. So for the last part of this video, we're going to ask, well, how do you know if you found solutions, and how do you know if you didn't find solutions? Okay, so it's not going to happen, of course, that we will find solutions to our system of equations. So far, so good. In our last video, we saw this system and we got a whole bunch of solutions. Okay, so we have a free variable z, so you have an infinite number of solutions. So what we're going to do is we're going to play with this system and see what happens. We're going to change the third equation. Change the right side of the third equation to a 0. Okay, so of course that corresponds to this augmented matrix, also with 0 over there. I'm going to erase the bars, here they are, so that we can run this on Maple. So, compute matrices REF. Okay, so this is now a very different REF from the one we got before. Okay, so notice that in the final row, we get 3 zeros followed by a 1. Okay, but remember, there's supposed to be a bar between the third column and the fourth column. So really, the last row says that 0 times x plus 0 times y plus 0 times z equals 1. Okay, now wait a minute. We get 0 on the left, 1 on the right. And of course, this is false. Okay, so therefore, there are no solutions to the system. Okay, so we're going to do one more thing. We're going to keep that 0, and then we're going to change the coefficient of z from 5 to 6. So that will be a 6, and that corresponds to this augmented matrix. So we're going to do the same thing. Let's make a copy of that down here, erase the bars, and then find the REF. Compute matrices REF. Okay, so we don't get 0, 0, 0, 1 this time around. Okay, so do these 3 rows all make sense? Well, we have 1 times x, no y, no z, equals negative 2. X equals negative 2. And in the second equation, we have no x, y, no z. So y equals negative 2. And finally, in the third equation, we get z equals negative 1. So we do have a solution, and in fact, there's only one solution. We get a unique solution to the system. So we went from no solutions in part A to a unique solution, exactly one solution in part B. So there are a couple of things I want to generalize from these 2 examples. The first example was a demonstration of what we call the inconsistency test. A linear system is inconsistent, which means it does not have any solutions, if and only if the REF of the augmented matrix, which represents that system, contains a row made entirely of zeros except for a 1 in the final column. And when that happens, that 1 in the final column is actually a leading 1. The second example produced a special kind of matrix called the identity matrix. So in an identity matrix, you only get ones and zeros, and in fact, all of the matrix is made of zeros, except for ones which appear in what's called the main diagonal of our matrix. Another way to think about it is that in column 1, you see the vector 1, 0, 0, everything else 0. In section 1.1, that was called the vector E1. And there are n of these vectors in every Rn. They're called the standard basis vectors. So E1 appears in column 1. In column 2, you have 0, 1, everything else is 0. So that is called E2, and so on. On the nth and final column, you have all zeros except for a 1 at the very bottom. That's called the vector E sub n. So to remind us of what happened, I copied only the first 3 columns of our augmented matrices in part A and part B. Let's find the REFs. Compute matrices REF. How about the other one? Compute matrices REF. Okay, so this is our special identity matrix. Column 1, 1, 0, 0. Column 2, 0, 1, 0. Column 3, 0, 0, 1. This is not an identity matrix, but I do want to point out something special though. We have one row of zeros, but we also see 2 leading variables and 1 free variable. Okay, so let's think about that. You have 3 rows and 3 columns. What happens if you have 1 row of zeros? It means that you have 2 leading ones and 1 free variable. What happens if you have 2 rows of zeros? Well, it means you only have a single leading one and no, not 1, but 2 free variables. So we can generalize that to what happens to the REF of any square matrix. If you have an n by n matrix, then exactly one of the following 2 possibilities happens to the REF. You will either get the identity matrix, IN, or you will have an REF that contains at least 1 free variable and at least 1 row of zeros. But if there are R leading ones, then the number of free variables is of course n minus R, because any variable which is not a leading variable is a free variable. This is also the number of rows of zeros in your REF. This number R is special. It is called the rank of our matrix, and it will appear several times in the near future. All right, so lastly, let's summarize what we did. How do you test in general whether a vector is a member of the span of a set of vectors? So you have S, V1 through Vn, a non-empty set of vectors from Rm, and B also from Rm. Form the augmented matrix. So we pointed out that after you set up that system of equations and then convert it to an augmented matrix, the first vector appears in the first column of your matrix. So you assemble the augmented matrix with the first vector in column 1, the second vector in column 2, and so on. And then you have B on the right side of this augmented matrix. Apply the Gauss Jordan algorithm, or even better, if you're doing it by hand, choose wisely what your row operations are going to be. In any case, look for the REF. Then what happens? Our vector B is in the span of S, if and only if a leading one does not appear in the rightmost column of the REF. And as we said, this is another way of saying the inconsistency test. Furthermore, in the case when B is in the span of S, there are an infinite number of ways to represent B as a linear combination of V1 to Vn, if and only if there is also a free variable in our RREF. Alright, so that is our video for today. Thank you so much for watching. Again, you will find me and the 4th edition on Facebook and of course at kendallhunt.com. Until next time, enjoy the rest of your day.